Greetings, welcome to Electronics2. This is lecture number 40 and I am Razavi. Today we will wrap up the 4 feedback topologies that we've been talking about and we've been trying to study. In particular, we're going to look at the current feedback as the last topology. And then we will take a look at applications of feedback in one domain of electronics, which we call power management. And we'll see that it has some important and interesting role that it plays in this domain. And then we go on to a difficult problem in feedback circuit analysis, namely the problem of loading, something that we have so far swept under the rug and tried to avoid, but in real life we cannot. So we'll have to develop a methodology for analyzing feedback circuits when this problem exists. Okay, but let's remember what we did last time. We finished up with the third feedback topology, namely current voltage feedback. And we saw that the feed-forward amplifier generates a current in response to a voltage. So we call this a transconductance amplifier with a gain of Gm, and the feedback network measures this current and in response to it, in proportion to it, generates a voltage here. And now these voltages have to add up in series and be applied to the feed-forward amplifier. So we saw that for K, not to disturb this current, its input impedance has to be 0 in the ideal case. And the final conclusion that we drew was that the overall output impedance of this circuit is given by the output impedance of the open loop amplifier multiplied by 1 plus the loop gain. So the output impedance goes up because the circuit wants to become a better current source. And if you remember, in this particular case, we said that to measure this output impedance, we have to cut this wire here and place a voltage source Vx and then measure Ix. That is the only sensible method of defining and measuring the output impedance of this circuit. All right, so today we'll look at the fourth topology, namely current feedback topology. So that's to be expected because we identified there should be 4 possible combinations. So here's our current feedback topology. So as usual, we draw the 2 systems, A1 and K. So here's A1. A1, we're trying to sense a current and return a current. So the open loop amplifier itself is a current amplifier. It receives a current and generates a current. So the current gain of that amplifier will be called AI. Like for voltage amplifiers, we called it AV. Here we call it AI. All right. And now the feedback network K must measure this current. So just like before, we have to cut this wire. Ordinarily, the current just flows through this wire, right? So we cut this wire and insert K into that wire. And hopefully, the input impedance of K is very low so that this wire doesn't know that we cut it and we try to measure the current. Okay, and then this goes back and we are returning a current, not a voltage. So our input is a current source like this, I in. This current source wants to go to the main amplifier like that. But then we want to subtract the feedback current from it. So we connect it like so. Okay, so we're drawing a current here in proportion to that current. So let's say the output current is 1 milliamp, 1 milliamp of signal, 1 milliamp of sinusoidal signal. And then this return current is maybe 0.2 milliamps, 1/5 of the output current, right? Okay, so that is the current feedback topology. And as usual, we would like to find the output, the closed loop gain, the closed loop input impedance, and the closed loop output impedance. Now, this circuit doesn't have much application in real life, so we won't bother going through all the details as we did before for all these other three topologies. I will just give you the final results. And the final results should be predictable anyway, because we know that if we are sensing a current at the output impedance should go up because we're trying to build a better current source. And if we are returning current to the input impedance should go down because we're trying to build a better current sensing device. So our prediction is that the closed loop gain, I out over I in, is the open loop gain, the gain of this guy, divided by 1 plus the loop gain, right? 1 plus KAI. So that's true for any negative feedback system. And then the closed loop input impedance, closed loop input impedance should be how much? It should be the original input impedance of AI, which we usually denote by R in. Okay, when we bought this amplifier, it has a certain input impedance. And now, because we are returning a current, the input impedance goes down by 1 plus the loop gain. So this gets divided by 1 plus the loop gain. Okay. All right. And finally, we have the output impedance of the circuit, which again should be obtained by cutting this wire here, placing a voltage source here, and measuring the current that flows, right? And the closed loop output impedance is equal to the output impedance of the original amplifier. So again, when we place a short circuit here, we open that, we cut that, put a voltage source here, measure that output impedance. That's some output resistance, or out. And that gets multiplied by 1 plus the loop gain. So I have to do that because we're trying to build a better current source. Just like before, it becomes R out multiplied by 1 plus KAI. Okay? So that's all really we want to cover here. We won't go through examples of the circuit. As I said, the circuit doesn't have too much application, so we won't worry about it. All right. So this concludes our study of the 4 feedback topologies. And now I would like to talk about some applications of these various ideas that we've seen in power management. Now, what do we mean by power management? So let's write here applications of feedback. By feedback, we mean negative feedback in power management. So the field of power management deals with controlling the power supply voltage, the power supply current, and the amount of power we draw from the supply voltage for a given system. It could be a mobile phone, it could be this camera that is recording this video, it could be any device, right? Any device that has certain power requirements, and we need circuitry there to control all these things. I will show you examples as to why we need to control things. You might think that what's the big deal? I just take a battery like this, right? That's my battery, I hook it up to my circuit, and I'm done, right? So in fact, this microphone connects to a transmitter, and that transmitter has one of these batteries in it. So why do I need power management, right? But I will show you some examples that the actual situation is not that easy, and that's why we need to have power management. Okay, so let's start with one example of power management, which we call voltage regulators. And in fact, when we started the discussion of feedback some lectures ago, I did show you an example of a voltage regulator circuit, right? So we are returning to that. Now, what does that mean? Well, so here's a mobile device. So let's say your cell phone or something, right? Mobile device. And this mobile device needs to be powered up, right? It needs to have a certain amount of voltage across it. Okay, so we built all the circuitry in here for a certain voltage. So let's say we would like to have 2 volts here. Okay, now I connect this mobile device to a battery, right? So let's say a battery like this. Now this is a 9-volt battery, but you might have another battery that typically has a value of something like 3.6 volts, and we call this VBAT. Okay, this is actually several batteries in series. All right, so the first issue that we see is that this is 3.6 volts, that's 2 volts. So somehow we have to convert this to here. Okay, so that's one issue. The other issue is that as this battery, the rechargeable battery in some device, begins to discharge, this voltage drops. So initially it's 3.6 volts, then it discharges, goes down to 3 volts, maybe 2.7 volts, maybe 2.5 volts. So for this entire range of changing voltage here, this device must see a constant 2 volts. Okay? So in other words, I can't just put a resistive attenuator between this and this, right? So even if I say, well, 2 volts over 3.6 volts is some amount, so I just build an attenuator, which would not be a good idea anyway. I put an attenuator between here and here. The problem is that I need a constant voltage here, but this voltage is not constant. Okay, so here we apply a feedback system, and this is how it goes. All right, so I need to put a device between these 2 points, obviously, right? Because I have 3.6 volts here and 2 volts here. So what do we put there? It cannot be a 2-terminal device. Because if a 2-terminal device, like a resistor, then we don't have control over it, right? So we need a device that can be controlled. Why does it have to be controlled? Well, because when this drops to 3 volts, I still want to have 2 volts here, so I have to change this. Right? If it's the same device, I cannot use it for 3.6 here, 2 volts here, and then 3 volts here and 2 volts here, and then 2.7 volts and 2 volts here, right? It won't work. So it has to be a 3-terminal device. What 3-terminal devices do we know? Transistors. So let's use a MOSFET here, an NMOS, for example. Is an NMOS device, right? And my hope is that by adjusting this gate voltage, I can make sure that this is always 2 volts, even though this has some changes in it. All right, so how do I do that? It has to be automatic, right? This should be a feedback system. Okay, so we will take this voltage, which we want to measure. We want to sense this voltage and make sure it's 2 volts, right? So I will divide it up and I will compare it with a reference voltage. Reference voltage. So in the simplest case, let's say this is 1 volt and these two are equal, right? Then that has to be 2 volts. 2 volts divided by 2 gives me 1 volt. I compare and then I control this MOSFET. This amplifier has a gain of A0 and this has to be minus here and plus here. All right, this is what we call a voltage regulator. So how does it work? Well, the idea is that because you can think of this as the input of the system, right? The input is constant. What this feedback system wants to do is it wants to make sure that the returned quantity, the feedback signal, remember U is this. It wants to make sure that this is very close to this. It's a good copy of this. So if the input is 1 volt, this is also 1 volt, right? If this is 1 volt, how much is this? Well, these are related by only the ratio of these resistors, so that has to be 2 volts. So no matter what happens, no matter what voltage we have, this goes up and down and so on, right? This voltage wants to stay at 2 volts because this voltage wants to stay at 1 volt. Okay? All right. So here comes the quiz. All right. So let's suppose that this voltage is constant, okay? It's a good battery, it's not changing. But let's suppose that in my mobile device, the mobile device was off or it wasn't working, doing anything. So it's drawing a small current here, right? It was drawing a small current. But then I turn it on or I'm making a phone call, so suddenly it has to draw a lot of current because I'm transmitting a high power, right? So the current, we can call this I sup. The supply current, I sup, goes from, let's say it used to be 10 milliamps, now it goes to 100 milliamps. Okay, here it wasn't doing much, it was just sitting there with all the apps on it and so forth, and then I dial the number, I'm making a phone call, so it's drawing a lot of current, 100 milliamps. So how does this loop respond to that? Okay, so we are trying to draw 100 milliamps from here. This voltage probably wants to drop, right? Anytime you want to draw a current from somewhere, it wants to drop. So how does this loop react to such a situation? I'll give you 1 minute to think about it. Okay, so what do we have here? Well, let's call this voltage V sup. So what we see is that V sup drops, right? So V sup wants to drop because we're trying to draw a large current. Right, we're trying to draw a large current here, and this voltage wants to drop. Because this voltage is produced by the MOSFET. The MOSFET has to carry more current. It wants to have more VGS. It wants to have more VGS. This voltage wants to drop. Okay, this voltage wants to drop. So what happens to this voltage? Let's call this node P. We see that VP drops, right? This voltage drops. The op amp says, my inverting input has dropped. So what should happen? Its output should go up. So Vx, this one wants to go up. So Vx goes up. Vx goes up and it turns on this MOSFET more, right? Because now you want to have a bigger VGS so that this transistor can still support 100 milliamps of current. So VGS of the MOSFET goes up. It goes up enough so that the MOSFET can deliver 100 milliamps while maintaining 2 volts at this point. Okay? So after the loop settles again, after the loop goes through all the iteration that it needs, it converges such that this is still 2 volts, this is still 1 volt. This voltage has changed, right? This is no longer the old voltage because the MOSFET now needs to deliver 100 milliamps, not 10 milliamps. All right, so that's how this loop works. Sometimes we call this a servo loop. So we call this a servo loop. All right, so you can see that here we are managing the current and the voltage delivered to this device by this simple voltage regulator. All right, now this MOSFET can operate in one of 2 regions. So MOS device can operate in a triode region. So in that situation, it becomes like a voltage controlled resistor. So as a voltage controlled resistor. That makes sense, right? What I'm hoping is that I have a resistor between here and here to drop this difference, right? This is 3.6 volts, that's 2 volts. I need a drop of 1.6 volts. So I have a resistor from here to here. But the resistor is variable. So when this guy wants more current, I reduce the resistance and vice versa. Or if this voltage goes up and this voltage has to be 2 volts, I increase this resistance so that I have more voltage drop, right? So that's why it's a voltage dependent resistor controlled by this feedback loop. Okay, or B, in the saturation region. In that case, in the saturation region, meaning that this voltage is not too low, right? The drain source voltage has to be large enough, so the device is in saturation. In that case, you can think of this as a source follower, right? You see, the gate is controlled and the source is going to the circuit. So you can think of it as a source follower. So as a source follower. Okay? So depending on what we're trying to do, we might choose this option or this option, but those are the 2 possibilities. All right, so that's one example of power management. Let's talk about one more, which is also interesting, and we'll call this current regulation. Now we have a different problem, and it's an interesting problem. So you have a mobile device, and inside the mobile device there's a rechargeable battery, right? So here's a rechargeable battery. So we'll call this a rechargeable battery. Okay? All right. Now, how is this battery charged? Well, we have a charger. You plug in the charger into the wall, and you hook it up to the device, and now the device is, the battery inside the device is being charged. All right, so the charger that we hooked up to the wall and is responsible for charging this can be modeled as a voltage source, right? So here's another voltage source, which we call V charger. Okay? All right, so these two need to be hooked up. All right, so we're going to connect this here, and we want to connect these two. So this battery is discharged. We have used up the battery inside our device, and now we hook it up the charger, hook it up to the device. This battery needs to be charged by the charger. Well, here's the problem. Let's suppose that this charger produces, for example, 3 volts. And this battery was charged, but this charged a lot, right? So you have only 1 bar or less on your phone. The phone says your battery is really low. So this could be, for example, 1 volt. It used to be 2 volts, now it's 1 volt. It's discharged to 1 volt. Can I just short this to this? No, that's not a good idea, okay? If you place 2 voltage sources in parallel, what happens if they have different voltages? Well, a lot of current has to flow, right? Ideally, an infinite amount of current has to flow. So when we have a situation like this, where this is only 1 volt and this is like 3 volts, we can't just connect them together, because a very large current will flow, and that current will damage this rechargeable battery. All right? At least it will shorten its lifetime. So we don't want to charge a rechargeable battery with a constant voltage. Okay, this voltage here. We don't want to do that. What we would like to do is charge a rechargeable battery by a constant current. Okay, so it starts out, it has 1 volt on it, we start injecting some current, right? 20 milliamps, 50 milliamps, gradually just charging it up, right? Until the voltage reaches what we want, and at that point we stop. All right, so the idea is that I need to have a current source to charge this. Let's put a P-type current source up here. Okay, so this actually goes to the charger, right? That's a current source. Okay, now I want to make sure that this current is well defined and constant. So I will need to measure the current that flows through the battery, this rechargeable battery, right? How do I measure that current? Well, remember, to measure a current, we're going to cut that wire and place a very small resistor in series with the wire. So I will cut this wire here. Let me change the color. I'll cut the wire here and place a resistor. We call this resistor R. So now, whatever current we have, so we call this I bat, the battery current, flows through this R and gives us a voltage. We're going to take this voltage and compare it with the reference. And then the result goes and controls this current source. In this case, this should be positive, this should be negative, because we would like to have negative feedback. So how does this operate? You can see that we have a charger here. The charger is 3 volts or something, it doesn't matter. This is the supply of this current source. This current source says, I need to deliver a certain current. How is that current defined? Well, I battery flows through R, so this voltage is R times I battery, right? And again, thinking of this feedback loop as sort of, this is the input and this is the feedback quantity U. The feedback loop wants to make these two very close to each other. It wants to minimize this error. So this voltage needs to be equal to Vref, right? So that means that the current flowing through this branch, I battery, is well defined, right? Is equal to this voltage, which is Vref, divided by R, little r. So now, given that Vref is provided by us, and it's a good voltage, it's a constant, well-defined voltage, and hopefully R is also a good, constant, well-defined resistance, this ratio tells us how much current we are applying to the rechargeable battery to charge it up, right? And that's what this loop does. This servo loop wants to make sure that this voltage is a good copy of this, which means this current satisfies this equation, and we know how much current we are applying to the battery. This is another example of power management. We're managing how this battery should be charged up from the discharged state. Very well. So this concludes this little study of power management and how feedback is useful there. Now we're going to the problem of loading in feedback circuits. All right, let's go to the next slide here and talk about this problem. Okay, so here's the situation. Problem of loading in feedback circuits. So we have seen this problem to some extent in the examples that we studied in the past, but we try to avoid this problem by making some assumptions. So I'll show you some examples and see where that problem comes into the picture, and then eventually we have to solve it. Okay, we have to see how we can deal with this problem. Okay, so let's go over some examples of how this problem arises. So here's one situation where we had something like this. RC V in. So we are here. This is our standard feedback system. X, Y, A1, K, positive, negative, right? And then we wanted to build a voltage feedback system. So we identified this whole thing as a circuit that has two inputs and one output. So we said, okay, this circuit has two inputs and one output, so that's A1, right? And then for K, we just decided to use a voltage divider. Right? This can be a MOSFET or a bipolar device. Doesn't make any difference. All right, so now we have some problems here that in our analysis we sort of avoided. Okay, so what are the problems? The problems arise when we try to look at the open loop circuit. Remember, the closed loop parameters are equal to the open loop parameters divided or multiplied by 1 plus the loop gain. So we do need to find the open loop parameters, right? We need to find the open loop gain and input impedance and output impedance. And one more thing we need to find is K, the feedback factor, or the loop gain, K times A1, one of the two. We have to find that, right? Okay, so here are the complications. Let's try to open this loop. How do I open it? I'm looking for the open loop amplifier, right? You say, well, the open loop amplifier should be this one plus that one, right? This is what we started out with. But is that really true? So here's the open loop amplifier, RC, and Q1. I'm thinking this is A1, right? But is that really true? In the actual circuit, if Q1 generates a current, a small signal current, not all of it flows through RC. Some of it is lost here. That's not reflected in this open loop calculation, right? It's not reflected in the open loop calculation, and it's not reflected in the closed loop calculation, because if you remember, we assumed that R1 plus R2 was very large. So this current was negligible. If R1 plus R2 is not large, how do we deal with the situation, right? It seems that there should be something here that models the fact that R1 and R2 load this node, right? We didn't mean them to load the node, but they do, because they have a finite resistance. So how exactly should this be connected here, right? We don't know. Something has to go in here in the open loop circuit to show that ultimately, when we go to the closed loop circuit, some of this current is lost. So you see that this affects both the gain of the circuit, the open loop gain, and the output impedance. You see the output impedance is changing if I have this or if I don't have this. So we have to think about the open loop gain, AV, how much is that? And the open loop output impedance, how much is that? We have problems in both of these. And there's one more issue, and that has to do with the input impedance of the open loop circuit. So when I'm trying to find this Rin, what do I do with the space? We said, oh, we're AC grounded, right? But is that really true? Because in this case, you see that this base is driven by some sort of resistance. So it's not exactly AC ground in the closed loop case, right? The point is that the impedance that we see here has some contribution from what we have in the base. We know that some impedance in the base will be divided by beta plus 1 when we see it from the emitter. So something has to go here also. We don't know exactly what to model that. Okay, so that Rin for the open loop circuit is a proper representation of what happens when we close the loop, right? So this takes a bit of time to get used to, that these components R1 and R2 are, of course, appear in the closed loop circuit, but they do need to be included in the open loop circuit so that their loading is properly represented, right? R1 and R2 load RC. R1 and R2 also, in a sense, load the input in a very strange way. So we want to include these properly. Okay? All right. So that's one example. Here's another example that we saw before. We built a two-stage amplifier. And we said, okay, I need to return this voltage. So I again divided it down. And again, I'm thinking of this whole circuit as this subtractor plus this amplifier, right? So, and this is my K, so I just bring it back like this, right? And I'm thinking, okay, this is V in and this is V out. Well, we saw this before. Now, when I open the loop, so let's say I cut the loop here, and I say, okay, now this is my amplifier A1, and this is my K, right? Well, okay, so obviously K again is loading the output here. So this is RC2. Now we have something here loading RC2. We don't exactly know what. And the other situation is that this input impedance for the open loop circuit is not just R pi. So let's go and draw the open loop circuit. So we have something here. Again, we don't know exactly what. That should be connected to the output node to represent the loading of the feedback network. And then it seems that now this emitter is not at AC ground, right? It's, this emitter is degenerated by the resistance that we have here. Okay, so something has to go here as well, we don't know what, to model the fact that the input transistor is degenerated by the feedback network. That was not the intention of the feedback network, right? The intention of the feedback network was to bring a voltage here. That's all. Because this guy is a voltage subtractor. So, in fact, if we had an ideal voltage amplifier or unity gain amplifier, an ideal voltage source here, this would be perfectly happy. It would subtract these two voltages, and it would not be degenerated by anything because this output resistance is 0. But unfortunately, this is not a good voltage generator, right? Its output impedance is not small, So because of the output impedance of this guy, this is being degenerated. All right? Okay. So we can summarize these things. Let me give you one more example and I'll summarize. Here's one more example that we saw before. So remember that we wanted to build a transimpedance amplifier with a current input and a voltage output. So we said, oh, we can just connect a resistor from the output to the input, and that will serve as the feedback network, right? It takes the output voltage and generates a proportional current and returns it to the input. Okay, so again, the same problem happens. This RF is loading the output node, and it seems to be loading the input also, right? If the current's coming in, not all of it goes this way, some of it goes this way. And that's again not something that we had intended to do. So we have a problem here. So if you draw the open loop circuit, I'm trying to find the open loop parameters, the open loop input impedance and gain, and the open loop output impedance, right? And so this goes to AC ground, that's fine. But then I don't know what to do here, right? So this RF might have some effect here. I don't know what. And it will have some effect here. And I don't know what. Okay? So all of these issues can be summarized as follows. What is really happening is that when we have A1 and K, and these are connected like so. So let's see, I'll give you one example of voltage feedback because that's easier to see. So we have we are sensing a voltage here and we are returning a voltage here, right? Okay, so the difficulty is this. The difficulty is that the input and output impedances of A1 and K are not the ideal values that we thought, right? For example, this output impedance should be 0 because this is supposed to be a good voltage amplifier. But it's greater than 0, right? Or out. And this input impedance is supposed to be infinity because we are trying to sense a voltage like a voltmeter. But it's not. So this is less than infinity. So what happens when I connect this to here? This has a finite output resistance. This has a finite input resistance, not infinity, this. So when I hook this up to this, then the conditions that we use to analyze the circuit no longer hold. So the results that we derived no longer hold. Okay? All right. Similarly, we assume that in the ideal case, the output impedance of the circuit should be 0 because it's trying to deliver a voltage. But in reality, it is greater than 0. And this input impedance is supposed to be infinity because this is sensing a voltage, but in reality, it's less than infinity, right? So Rin is less than infinity. So again, when we connect these together, the conditions that we use to analyze, for example, the gain and the input impedance and so forth are not correct anymore. So we have this loading effect, loading here and loading here. All right, so these are the issues that we face. Okay, so as we go along and as we try to analyze these circuits more carefully, hopefully these problems become more obvious and you will see why we can't just avoid them in real life for an actual circuit designed. We have to be able to include these effects, but we need a methodology so that the analysis is still manageable and we don't have that much complication in our analysis. Okay, so let's go ahead and calculate, look at one more example of case is like this. Let's see. Okay, here's another example that we faced before. So when we looked at this circuit before, we said it takes a current and generates a voltage, right? So all it is that we have an amplifier here with one input and one output. That's all, right? And then we are injecting a current, and there's a feedback resistor that provides a current for the input. So we said maybe we can just simplify this to this. Here's an amplifier. It has one input. It has to be an inverting amplifier for the feedback to be negative. And then here's a resistor, and here's what we get, I in and RF. And we said, yeah, this is a good feedback circuit. We call this like every other one of these. This is a TIA. This is a TIA, right? It's a transimpedance amplifier. And it's very simple, at least conceptually. We just have an op-amp with a feedback resistor. Well, we have similar problems in breaking the loop, right? How do we break the loop? Okay, well, let's try to break it like this. I have I in and what do I do with RF? RF, so I open it like this, right? RF. So what exactly should I do here? Should I just take RF out because I have broken this loop? Should it be there? You can see that if I take RF out, something else goes wrong in this case. I in needs to flow through a very high impedance. And then we're still trying to find V out over I in for the open loop circuit, right? Which we denoted by R0. So R0 is equal to V out over I in. But we see that in this case, if I don't have RF at all, this current wants to flow through a very high impedance. We generate a very high voltage here. That voltage gets multiplied by this A0 and so on. Things don't begin to make much sense in this case, right? So there are all sorts of issues like this when we try to open the loop, when we try to find the open loop parameters of the circuit.